I also want to point out that if you keep going farther and farther away, so L becomes extremely larger than S. Not just much more than, but extremely large. So as L goes to infinity, this goes to 0. To give us some sense that we've done something right, because if I get farther and farther away, I really can't differentiate the distance between those two, and it just looks like I've got some neutral charge there. I got a positive and a negative. So if I get farther and farther away, it makes sense that it would go to 0. In terms of mathematics, at what point can you assume that you're far enough away? What is L L being much greater than S? If you needed a rule of thumb, generally the 10% rule. So if S is less than 0.1 of L, that's typically the cutoff.
You said L goes to 0?
No, if L goes to infinity,
Oh, yeah.
the electric field goes to 0. Here we go. By the groundswell, by the incredible desire to see calculus. Let's do some calculus. Any other questions before I continue erasing?
So this is why in your original universe analogy up there, like if it was like across the universe or something, you wouldn't experience any, you wouldn't notice it or whatever, like you said, because L would be infinity, the electric field would go to 0.
Yeah, pretty much.
Just gonna keep it.
I mean, from an engineering point of view, yeah, you can get away with the distance between the two charges is nanometer on 5 meters away, good enough for infinite distance.
Oh, really? It's that close?
Yeah, well, if you think about an atom, it's on the order of nanometers. From a physics point of view, yeah, you probably can get away with that for most situations, but if you're studying the effect of the electric field, then you probably don't. But you've got the multi-million-dollar equipment to sort of measure that kind of stuff. Start out with a simple one. I have a line of charge of length. I'll stick numbers in here, 3 meters. And the linear charge density is uniform. And we'll say 2 nanocoulombs per meter. And I got a point out here. We'll make that 4 meters, obviously not to scale. And I want to know what is the electric field at point P. We have a distribution of charge. Calculus is involved. Because I can't simplify this. I'm not so far away from it that I can treat it like it's a single point. I'm close enough to it that I have the distribution matters. So once you recognize that calculus is involved, well, we figure out the electric field based upon a tiny little segment. So what I'm going to do is I'm going to take a tiny little segment here, dq, and I'm going to look at the electric field at point P because of that. Now, I have that distance will vary because I know dq, the position of DQ will be anywhere along this 3 meter stretch here, so I have to define another unknown in here. Why don't we call this X? If you want to define X from here, that's fine. There are many different ways of doing it. I'm just gonna make that distance X.
What does lambda signify?
The uniform, it's the linear charge density. It's the charge per unit length. So that would be equal to dq dx, which is equal to q over, call that L. It's uniform, so the differential, the dq dx would be the same as taking the entire thing divided by L.
So it's the amount of charge per given unit.
Yeah. Lovely. All right, I got my electric field. First off, I know that this is a positive charge because I have a positive charge density. What is the direction of the electric field at point P? All right, it's all two fingers pointing in the correct direction. And one rebel, two rebels. What is the direction of the electric field at point P? If this is positive, if this is a positive charge distribution, what is the direction of the electric field here? All right, so we now have these people who are pointing all in the same direction that way, because it goes away from the positive charge. If this is positively charged, the electric field goes away from it. So it's a one-dimensional problem, so I'm just gonna say to the right is positive. If you really don't like doing it that way and wanna make it the hat direction, go for it. It's gonna be equal to, technically, the differential of E is gonna be equal to K sub C dq over r squared. Well, actually, I made that distance X over X squared, and it's positive direction.
So we take the integral of that?
Except X and Q are both variables. I know Q is a variable because it's dq, and if Q were not a variable, then this would be 0. X is a variable because it depends on where dq is, so I have to get it in terms of a single variable.
Or double integral?
True. Single variable is just so much easier here.
Sure. I just want to see the doubles and triples.
Well, I can connect the two using this relationship here. I know that my linear charge density is equal to dq dx. No, lambda is equal to dq dx. And so dq is equal to lambda dx. So I'm left with kc lambda dx over x squared. Now I've got my single variable. Integrate. So I have kc lambda integral of x to the -3 or -2 as kids they say dx. And now my limits of integration. What is the smallest value of x?
0.
No.
Infinity?
Pardon?
Infinity?
No.
0. 7. No, smallest? 0.
Smallest.
Would it be negative?
No.
Oh,
Zero.
the smallest would be how much it is over there.
But the smallest would be 4. It'd be 4. X is the distance from here to wherever my differential is. The smallest, this is where the charge ends, right here. The smallest x's can be is 4 meters,
Would the biggest be 7?
and the biggest would be 7. So the only thing separating Ibrahim from the correct answer earlier was time. You were just unstuck in time.
Yeah.
So now, I got kc lambda. Let's see, add 1. divide by one, from 4 to 7, and that is a 4 there. Which is what I had written before, but it looked kind of like an X. And so I've got negative KC lambda 1/7 minus 1/4. We'll end up with a positive answer, because what I have in parentheses here is a negative number, and that negative number will cancel out. If we'd ended up with a negative number in the end, we know something would have gone wrong, because we know, we think through it, we know that it's gotta be in the positive direction, the way I define positive. And so we have negative 9 times 10 to the 9th times lambda 2 times 10 to the negative 9th times whatever 1/7 minus 1/4 is. .9, 1.93 units.
Nanocoulombs, not nanocoulombs. Newton coulombs. Newtons per coulomb.
There we go. Just have to talk it through.
Where did you get the 9, the 10, those first two numbers?
That,
Then the one after it, yeah.
that's Coulomb's constant.
Yeah, and then,
And the number after it, that's the linear density, which I wrote right there.
okay.
The nano 10 to the negative 9.
And then coulombs, you just kept it there in the answer, coulomb.
The units here would be Newton meter squared per Coulomb squared, times those units, which would be coulombs per meter, times these units, which is meters. Sorry, would be 1/meters.
Okay.
And so the meters would cancel out, one of the coulombs would cancel out.
Yeah, okay.
I do what you do and leave the units out until the end.
Yeah, and that's perfectly fine. You don't have to track the units as long as you, I mean, we're dealing with SI units to begin with, so I know I'm gonna have to do this.
This is thousand like tracks the units the entire way.
Yeah, that's more effort than I already spent.
Yeah, exactly.
Yeah, Nick,
What is a coulomb?
besides the unit of charge? When we did the Van der Graaf generator, just to give you some sense of scale, that is on the order of microcoulombs, 10 to the negative 6 coulombs. I can't remember the exact number that people have calculated in the past. But, yeah, it's on that order of microcoulombs. So imagine something a million times more powerful.
That's one coulomb.
That's 1 coulomb.
So if a microcoulomb could kill you, or no, I guess a coulomb couldn't kill you.
A coulomb could, a microcoulomb would hurt. Well, it depends upon how it's applied, but
I see.
1 coulomb charge is large, very large.
Okay, this is slightly on topic to the Van de Graaff generator.
Okay.
So hypothetically, if all of us were to hold hands except one person who's holding their hand on the generator
Right.
before it turns on, and they kick it on,
Right,
so everybody becomes positively charged.
right.
And then the person at the end of the line, like, high fives or like touches somebody that is coming in late,
There would be a shock.
there would be a shock.
Yes.
But
I
it
have
wouldn't
a
be
lab
as strong as if
experiment.
they just touched the.
Give it enough time, it should be. Reality, I'm gonna guess it's not quite as strong, but I think it would still hurt.
The body doesn't provide any sort of like, resistance or whatever.
Well, I mean, you've got, with shoes on, I mean, if you have rubber soled shoes especially, I mean, where's the charge gonna go? The charge is getting drawn from somewhere, so it gets drawn from the first person. Well, now that person is positively charged, so it's gonna draw electrons from the next person, and so on. So, given enough time, and I don't think it would take too long, I would think it would hurt just as much, but not really something I could test.
Would the line of people just keep building up charge as long as you left the Van de Graaff generator on, or would you reach a certain limit?
In theory, it would, the line of, you would, oh, there is a limit to how much charge it can build up.
No.
So, I mean, I could add 100 more people, and in theory, that last person would be just as charged as if one person were touching it. But there is a limit to how much, free particles, that's not the word I'm looking for. There's only so much charge it will pull, as long as you're not, I mean, if the last person stuck his finger in the ground, now you've got a very large supply.
What's that limit based on?
The limit's based upon the number of, I guess, free electrons you got.
In your body?
Yeah.
In everybody's body, I guess.
Yeah.
So you should have more of a limit than if you have more people. I guess, but it's spread.
No, because each person is getting, when the first person becomes positively charged, he pulls electrons from the second person. So, and so now you're constantly trying to fill in the void. So it should be, unless you've got some other source, if you just have people with rubber soled shoes on so no one's touching the ground, the limit should still be the same.
Yeah.
In theory.
It wouldn't get weaker, like as the line progresses.
In theory, no. In reality, I suspect yes.
Yeah,
You're just adding more charge from the Van de Graaff generator still,
yeah.
but then you have a limit with each person of how much. So you can reach that limit each time a new person is added, but it's the same limit every time, right?
Yeah. You know, part of my mind goes into how to test that, but that's testing with humans.
Well,
There's a
I
big
think
phenomenon
you
from
can
that.
also
I'm sure they'll be fine.
That's okay, we can write a scientific paper on it and make it double blind.
You know, just, okay, this
Make
is
it
the next
academic.
test. If you consent 100, if you don't, you fail.
I think that somebody might have a conversation with me about that.
I'll send them my way.
Well, they're running out of money, I consider being good.
Yeah, ever since that prison experiment happened, they really cracked down on doing experiments with students.
What?
The prison experiment in the, somewhere around 1970, where you, MIT?
Yeah, they had prisoners that, or well, people that were pretend prisoners.
And the people who were pretend guards.
Yeah, I
And
think I
led to
remember that.
abuse.
Yeah, we studied that in like high school.
Why did they do?
Ruined it for everybody.
What do you mean pretend? What do you mean pretend?
Yeah, you had students, some of the students, they were divided, some students were divided into, who were gonna be prisoners, others were became guards. And looked at the evolution of guards abusing. Eventually, guards abuse prisoners. Now, there's some question about how much of the aggression was created by Zaguri. Whatever, not Zaguri. The guy who did the experiment, there might be, I've heard some tales of some of the aggression was not natural, but encouraged by the professor in charge. Anyway, did you have a question?
Yeah, what's the difference between like a Coulomb and a voltage? Like the voltage of a generator or something?
A Coulomb is a unit of charge associated with a particle that is affected by a voltage. Voltage, in some sense, is like a pressure for that charge to move.
Okay.
So it's like, what's the difference between a water pump and water? The water pump would cause the water to move, or at least encourage it to move. Voltage would encourage a charge to move.
And so like the Coulomb is like the water in this scenario?
Yes.
Okay.
So 2NC over L for the lambda, is that like the standard, or,
That in terms of units,
yeah, just like the, yeah,
for a linear charge density, it's gonna be coulombs per meter.
and what the two come from?
I made that up.
Oh.
I just gave it to you. The two nano was just part of the problem. It's
Okay.
like, that's 3 meters, that's 4 meters, this was 2 nano.
Oh, okay.
Another variation of the problem is they give you the total charge and the length, and you figured that out.
Okay.
Alright, so on, I guess I'll see you in 2 days. Oh, I'm letting you out 2 minutes early apparently. Don't commit crimes in the next 2 minutes. Thank you.
But we can after 2 minutes?
After 2 minutes, you're no longer part of this class, so. I would say don't do it, but it's less paperwork for me.
Turn off.
Yes.
So